Welcome back to the exciting conclusion of section 5.3 on linear algebra and linear independence of vectors. So we've seen that in addition to arrows and matrices and polynomials, we also saw that functions form a vector space if they have their domain is negative infinity to infinity. And so we're going to talk about that function space, and we're going to deal with vectors in this function space, and each vector is himself just a function. Like f vector could be f of x, which would be x squared, and g vector would be g of x, which would be e to the x. Okay. Now, since there's so many vectors, we need a new way to check to see if vectors are linearly independent or not, and that is called the Wronskian. And to find the Wronskian for a set of functions, you take and first off list the functions in a row here, as many as you have, and then we take and we're going to do a determinant on him. So however many functions you have, you do derivatives on those guys until you get a square matrix like this, and take the determinant, and if the determinant is not always equal to 0, then, so if the determinant is not always equal to 0, then the vectors, in this case the functions, are linearly independent. Okay. So let's go ahead and do it for these two guys right here, x squared and e to the x. So we take and write our two functions, x squared and e to the x. We're going to make a determinant out of him, and so that he's square, we're going to need another row. So we'll take the derivative of these guys. Okay. And on a 2 by 2 matrix, the determinant is really easy. We'll get x squared e to the x minus 2x e to the x, and I can factor out an x e to the x, giving me x minus 2. Now notice that this will be equal to 0 if x is 0 or x equals 2, but it's not always equal to 0. So this Wronskian is not always 0, specifically when x is not 0 or 2, then the Wronskian is not 0. So because of that, we then know that our our two vectors are linearly independent. Okay. All right. What about for 3 vectors? Well, find the Wronskian for 1x and e to the x. Let's do this one together. So 1x e to the x, and we're going to make a determinant out of him. So we need to do some derivatives, and we'll do enough derivatives of the function so that we have a square matrix. And not only is this matrix square, but he is triangular. So the determinant will be the product of the main diagonal elements, which will be e to the x, which is never 0. Therefore, we can say that 1x and e to the x as a set are linearly independent. Okay. Now, one thing, the Wronskian does have a slight Achilles heel. If we do the determinant, and the determinant is always equal to 0, then the Wronskian test fails. Okay. So what I want you to do now is try one on your own. Check to see, by finding the Wronskian, whether the vectors x, sine of x, and cosine of x are linearly independent or not. Okay, so we set up our matrix with x, sine of x, and cosine of x along the top row. We do our derivatives until we get a square matrix. We then find the determinant. And I did a cofactor expansion along the first column because that involved a 0. So we'll do x times the determinant of this guy, which is negative cosine squared minus a sine squared. Then we'll do the negative times this subdeterminant, which would be negative sine x cosine x plus sine x cosine x, which is 0. And then plus 0, we don't care what he's multiplied by because that's 0. And when we simplify this, we find out that we get an answer of negative x, which is not always 0. So we know that the set of vectors, x, sine of x, and cosine of x, are linearly independent. Okay, so we'll see you in the next video for section 5.4.